So what kinds of solutions does this have? So without any constraints about X, there's going to be infinitely many solutions here. And generally for problems like this, there'll be two basic solutions. One comes from the inverse function, and then we translate that to get another, and then we can shift those solutions around. Depending on the problem, there can sometimes be even more basic solutions. So one way to go about this here would be to just first solve for the sign. So if I divide the 4 to the other side, I get the sign of 3x is equal to 3/4. And just to simplify this for a minute, I'm just going to call the 3x theta for a minute. So I'm just going to do a substitution and just say, well, what would the sign of theta tell me about the 3/4 here? So if I think about the unit circle, sine is a y value. So up here, roughly would be y equals 3/4. That's a 3 there. And that leads to this point here, or that point there. Now, the sine inverse only knows about solutions on this right side. So the sine inverse is going to throw this angle right there at me. Theta equals the arc sine of 3/4. Right? So that's some number. It's going to be less than pi over 2 for sure. Let's see, it's also going to be less than pi over 3. So that's one of the solutions. The other solution over here, let's do that one in blue. That blue angle there has a reference angle that matches theta, right? So its reference angle here is the same as theta. So if I go over to pi and then back up by that reference angle, my claim is to get to that point right there. I'm going to call that theta 2 for my other angle. That's going to be pi minus what the arc sine gives me. And by my picture, I know the arc sine of 3/4 is a positive number. So I go over to pi here, and then I back up by that same angle, but going clockwise instead of counterclockwise. So this one right here should be the other angle I want. So those should be the two basic solutions if it was just sine of theta equals 3/4. But I don't have theta, I have 3x. So what I have at this point now is for the green one, I have 3x equals the arc sine of 3/4. And then I have, for the red one, 3x equals pi minus the arc sine of 3/4. Now, these are both positive values. If I wanted the negative one, I would have to sweep in a negative direction. So we can talk about that in a minute. I'm not done because I need to solve for x here. So with this top one here, I would get x equals the arc sine of 3/4 over 3. And for this red one, I would get x equals pi minus the arc sine, all divided by 3. So that should be a second solution. And then I can keep generating more solutions here. Now that I've gotten down to talk about x, I want to think about the sine of 3x for a minute. So if I just consider the sine of 3x, that 3 changes the period. The period of this function is 2 pi over 3. So that's the new period. So I can extend either of these x values right here by just using the period. So if I needed other solutions, another solution, so let's call this, let's see, this one here can be x1, and this one here could be x2. So I can get another version of this one right here by just adding its period to get to it. So I claim that an x3 would be to take my x1 and add 2 pi over 3 to it. And I could keep adding multiples of 2 pi over 3. I'm going to keep getting more solutions. So let's check a couple of these and see how they work out. So I claim my first solution is the arc sine or sine inverse. You can type it either way, it depends on your calculator. Desmos allows me to just type arc sine. And 3/4. Make sure I'm on the right page there. Yep. So that is one of my solutions. And another version of that solution was to go pi minus that. So I think another solution is pi minus that number up there. Arc sine of 3/4. Oops, I lied. How did I lie? I forgot to divide by 3. So this one here, divide by 3. And this one here, if I divide by 3, it's going to screw it up. It's only dividing by the arc sine. So let's see, I guess I need to wrap this whole thing in parentheses and then divide by 3. There we go. All right, so there's the other one. So those are the first two solutions I found. Now then I claim if I take this one up here and I add the period once to it, I'll get another solution. So I'm going to give this a name so I can reuse it. I'm going to call this solution right here solution A. So I'm going to say A equals that. So then I don't have to type that again. And then down here, I'm going to say B equals that there. So another solution ought to be A plus the period. The period was 2 pi over 3. So that should be another solution right there. And I could keep adding multiples of that period. So I could double that period, and that should be another solution there, and so on. Let's test these out. So let's call this one solution C. And I can just generate these all day long, as many as you want. If you want me to go the other direction, then I would just subtract. So for example, I can say D is going to be either A or B. Take your pick. I'm going to take A. And I could subtract the period from that, and that should be another solution. Period was 2 pi over 3. So to check, I just plug back into my original equation and see what happens. So the original equation was 4 sine of 3x equals 3. So if I plug anything into this side right here, if it's the right answer, I should get 3 as the result. Let's try it. So 4 times the sine of 3, and I'm just going to do 3 times A, and the answer should be 3. And remember, A was my first solution up here. If I replace A with B, 3. If I replace A with C, I get 3. Replace A with D, I get 3. So again, unit circle helps us get, in the arc sine, the first solution. Then translation on the unit circle gives me a second solution. Then I finish solving the problem, in this case, divide by 3. And then if I just add or subtract the period to either of those first two solutions, I can get any number of solutions that you want. So if you say, hey, I need solutions for this that are from negative 2 pi to 0, then I would say, oh, okay, then I would take either of these and start subtracting that period to get some of those solutions. If somebody told me, find me the first 3 positive solutions, and I say, oh, okay, I'll take this one here. Let's get my highlighter. I would take this one here. I would take that one there. And then I would add on the period to this one to get the next positive solution. We can check those solutions by graphing. So I want to graph 4 times the sine of 3x, which gives me that crazy wave right there. And I want to know, let's say that's y equals, I guess I don't really need to say y equals there because it assumed it. But to get the other side of the equation 3, I definitely have to do y equals 3. And so then any of these intersection points are the ones I want. So for example, my solution A here, the point 283, that should be this one. And my B, the point 765, that should be this one. And then I added a period, so the point 2.377, that should be the next one. And from A, I subtracted the period. So this was A right there. Subtracting the period should put me here. So there's my negative 1.812. And you say, well, what about this one? Well, notice that one right there is to the, let's undo some of these. This point right here is to the right of that peak. So that would be related to this point right here. So that would be my solution B minus the period would get me there. Let's double check that. Let's come down here. So if I take my solution B, my second one, and I subtract one period, the period was 2 pi over 3, that should be negative 1.330. So there's that one right there. All right, so these take some getting used to, but we have a couple things on our side. One, we can use the unit circle to help us get a couple of solutions and then complete those solutions. Two, we got the graph. So the unit circle helps me get the first few exact answers, and then I can extend them and compare them to the graph to see if they match up. Let's try another.